This is the first video for Chapter 19. So Chapter 19 is on basis and dimension, and this is part 1. And remember that a basis is a set that spans the vector space and is also linearly independent. So you have a linearly independent spanning set. That's what a basis is. So for example, we have our standard unit basis. This is a basis for R3. You can see that it's linearly independent. If you made a matrix using these vectors as the columns, you have the identity matrix. Since it is reduced row echelon form of the identity matrix is the identity matrix, the columns are linearly independent. And you can fairly easily see how you can make the vector ABC out of these three vectors. You would just have A times this vector plus B times this vector plus C times this vector. That would give you a vector ABC. So this is a basis for R3. In general, E1, E2 through En is a basis for Rn. Similar reasoning, if you made the matrix whose columns were these vectors, you would have the n by n identity matrix, and you can fairly easily see how you would make the vector x1, x2 through xn out of these n vectors. So now what we want to do is, for example 204, show that this set is also a basis for R3. Now, we want to show that this set of vectors is linearly independent and spans R3. In example 192b, we saw that this set of vectors is linearly independent. So we need only show that this is a spanning set. So how do we do that? Let's suppose our vector ABC is an R3. Then, how do we make the vector ABC? How do we express this as a linear combination of these three vectors? We have, first of all, C times the vector 1, 1, 1. So that is going to get us the C as the third component. When we multiply C times this vector, it will give us C. But you'll notice it also gives us, if you multiply C times this vector, you have the vector C, C, C so far. So now we want to have linear combinations of the other two vectors that gives us ABC. So we add times the vector 1, 1, 0. And so now if we look at the second component, we have a C, then we have B minus C times the 1, and that gives us our B. And then finally, we have A minus B times the vector 1, 0, 0. And so if we add these three vectors together, we get the vector ABC. Since A, B, and C are arbitrary, that means that this set does span all of R3. We already knew it was a linearly independent set. Now we know it's a spanning set. Therefore, this is a basis for R3. We have one more example we're going to do in this video for part 1. And that is example 205. We want to find a basis for M 2 by 2. This is a set of 2 by 2 square matrices. And we want to find a basis for this set. And we're going to consider this set. It's sort of the matrix version of a standard unit basis for Rn. And so we have this set of matrices. Remember, these are vectors in the space M2 by 2. And so if we're going to claim that this is a basis for this vector space, what do we have to do? We have to prove that it's linearly independent, and we have to prove that it's a spanning set. So first of all, let's show the set is linearly independent. So what we're going to do is we're going to suppose that we can express the zero vector, which in this case is the zero matrix, as a linear combination of these four matrices, and show that all of our coefficients have to be zero. So let's suppose the sum of these four matrices is the zero matrix. The zero matrix in this space is what we would call the zero vector. So let's suppose that's true. Then if we add those four matrices together, so if we add these four together, what do we have? We have A, B, C, D, which is the zero matrix. Which implies A, B, C, and D are all equal to 0. And then finally, let's let X, Y, Z, W be an element of this vector space. Then X times the matrix 1, 0, 0, 0, plus Y, 0, 1, 0, 0, plus Z times the matrix 0, 0, 1, 0, plus W times the matrix 0, 0, 0, 1 is the matrix X, Y, Z, W. This shows that these four vectors span M22. We took an arbitrary matrix in M22 and we wrote it as a linear combination of these four matrices. It shows that these four matrices span M22. And I call these matrices because it's what they are, but we can also call them vectors because they are vectors in the vector space M sub 2 by 2. So that is the conclusion of the first video from chapter 19.